It was a body plot meter. For this transfer function, find what is the amplitude body plot, and also what is the phase body plot. A comment on pronunciation of the name. That's the way the mathematician from Wisconsin used to pronounce his last name, Bode. It's a Dutch name. In Dutch, it's pronounced Boda, according to Wikipedia, but in English also, according to Wikipedia, it is pronounced Bode. So let's find them. To find the one in amplitude in decibels, we notice that there is a double zero at 0, but what's the meaning of that? That signifies that the curve will enter climbing at a slope of 40 decibels per decade. That is good. We also realize there is a simple pole at 10 radians per second and another at 500 radians per second, so there are going to be two knees, two elbows, two kinks in that plot, one at 10 and another at 500. Each one of them reduces the slope of the curve by 20 decibels per decade. The curve is going to look like that. Enters climbing up at 40 decibels per decade because of the double zero at 0. And then at omega equals 10 radians per second, where the first pole is, the slope is reduced by 20 decibels per decade from 40 to 20. And I'll keep climbing all the way to the second pole at 500 radians per second, where the slope will be reduced again by 20 decibels per decade to a horizontal line. That is the shape of the plot. We need to fix it on the decibels axis. To do that, we need to determine the value of that curve at omega 1 radians per second, this value. At 1, the contribution of the two zeros at 0 will be 0. So we can determine this value as 20 log of 20 divided 10 divided 500, like this. 20 log of this 20 divided by 10 divided by 500, that is negative 48 decibels. Approximately, that is the value of the curve at omega 1. And once we have that, of course, we find out how many decades we move to the right. In this case, from 1 to 10, that is 1 decade. And being that we're climbing at a rate of 40 decibels per decade, we climb up 40 decibels, negative 47.96 plus 40 decibels. Well, we have approximately negative 8 decibels here. And then up to the next kink, we say, well, there is 1.7 decades between 10 and 500 radians per second. At a rate of 20 decibels per decade, that is a climb of 34 decibels. Negative 8 plus 34, that is 26 decibels. And we have already the amplitude body plot. For the phase body plot, the two zeros at 0 tell us that the curve enters horizontally at 180 degrees. Each one of those two simple poles will include two knees, this 10, 1 decade before at 1 and 1 decade after at 100, and the same for the 500 radians per second, 50 and 5000. We mark on an axis that is not up to scale those for frequencies 150, 100 and 5000 radians per second. And I'm going to include also the slope contribution of each one of them. This is a pole. That means that the first one is going to be descending at a rate of negative 45 degrees per decade. And at 100, we have the cancellation of that slope, positive 45 degrees per decade. And for the 500, the first slope is going to be descending because that is a pole. Negative 45 degrees per decade because that is a simple pole. And the second one at 5000 radians per second will cancel that out. And then we draw our curve. We enter horizontally at 180 degrees, like so. Bam. At 1 radians per second, we follow this curve down up to 50 radians per second, where the slope gets steeper. We go from negative 45 degrees per decade to negative 90 degrees per decade up to 100 radians per second. There, the inclusion of this positive 45 degrees per decade reduces the decline of the curve. We are back at negative 45 degrees per decade. And when we add this plus 45 degrees per decade, we bring that curve to a horizontal line. Let's compute now the values at different knee points. 180 degrees at 1 radians per second. Well, how many decades are between these two? That would allow us to compute the slope here, because we know the slope, 45 degrees per decade. If we know what is the distance in decade between 50 and 100, because we know the slope, that is negative 90 degrees per decade, we can compute what is this drop. And the same can be said. So between 100 and 5,000, and the drop between those two corresponding points. Let's compute that. The first one, 1.7 decades at 45 degrees per decade, that is a drop of 76.5 degrees. 180 minus 76.5 degrees, the value of the curve here is 103.5 degrees. The distance between 50 and 100 is 0.3 decades. But this curve is dropping at a rate of 90 degrees per decade, 90 times 0.3, and that is a drop of 27.1 degrees. 103.5 minus this drop gives us the value at this knee, 76.5 degrees. Last, the distance from 100 to 5,000, 1.7 decades. And the slope, 45 degrees per decade, dropping. So the drop from 100 radians per second to 5,000 radians per second is 76.5 degrees. 76.5 minus 76.5, that is 0 in degrees at this point. And that is the phase body plot of this transfer function up here. For the last part, taking both curves, we need to find what is the value of the transfer function at 1000 radians per second. Let's see it. 10, 500, 1000 will be in this zone. So the value of the amplitude of the transfer function at omega 1000 radians per second is 26 decibels. What about the phase? Well, 1000 will be somewhere around here. We need to find what is the value of the phase down here. Let's see. At this knee, the value is 76.5 degrees. The slope of this curve is 45 degrees per decade. And the distance between this knee at 100 and the point of interest at 1000, that distance is 1 decade. 1 decade, 45 degrees per decade. The drop is going to be 45 degrees between this point and that point. And that is the value of that curve is 76.6. Should be 76.5. There is a typo there. Minus 45 degrees. That is 31.5 degrees. And then the value of the transfer function, h at j1000 radians per second, is 26 decibels and 31.5 degrees. Thank you very much. This circuit has been as shown for a very long time. That phrase, as shown for a very long time, signifies that the circuit is in steady state. Because the source is AC, the circuit is in AC steady state, and we have a tool to solve circuits in AC steady state, phasor analysis. To analyze this as a phasor problem, well, the first thing we do is we identify the frequency, which is 400 radians per second. We continue reading. Find what is the current in the inductor as a function of time, the current in this inductor. B. Find the voltage in the capacitor as a function of time, this voltage. The first thing I do is replace this function of time with a phasor. 141, which is the peak value divided by root 2, gives us the RMS value, 100, 0 degrees. For the inductor, the reactance, not the impedance. For the impedance, I will add a J here, but not yet. 4 ohms. I write here J4. For the capacitor, negative J3 ohms. We're ready to solve the circuit to find this current, IL, and this voltage, VC. We can solve this circuit in many different ways, but the one I will use is divide this voltage by the total impedance of the circuit to find this current that will be both the current in the source and the current in the inductor. And now to find the voltage in the capacitor, to this voltage I will subtract the drop in these 4 ohms, J4 impedance, to find the voltage of this node, to this node here. And that voltage I will use voltage divider to find VC. The voltage divider will be that's a voltage divider that multiplies the voltage of that node, that is 100 minus a drop. There is a negative sign here that I didn't copy first. Now, those voltages and currents as functions of times are easy to write. 14,874 root 2 sine 400t, frequency is the same, minus 30 degrees and something. We write that as radians, of course. And the voltage in the capacitor has a peak value of this multiplied by root 2. And I convert that to radians. We're almost ready now. Let's evaluate this at t equals 0. For the last part of the problem, what is the current and what is that voltage at t equals 0? Well, we just make that 0 and evaluate that. This value times the sign of this expression and this value times the sign of this expression t equals 0. And the voltage in the capacitor at 0. What does the negative sign mean? Well, let's see. What that means is that this voltage actually is like so. 28.159 volts, like that. And that this current is actually flowing in the other direction. Allow me So this current here, let me make room here at the top. That current actually is flowing like this. 10,638 amps. To work on the last part, what is the active and reactive power supplied by the source? We multiply the voltage at the source 100 times the complex conjugate of the current in the source, which is the same current in the inductor which we found before. 100 times the complex conjugate of this current, that is the complex power delivered by the source, is 100 times the complex conjugate of this current, which is the same current in the source. That is 100 that multiplies 14,874 with an angle of positive 30,379 degrees, because it's a conjugate of this one. And we write this in rectangular form, which is 1283 watts and 752.2 vars. And that is the active and reactive power delivered by the source. Thank you very much. This is the first question for 25 marks, equivalent to quiz number 4. For the transfer function h of s below, and this one, find its body amplitude plot, both as an approximate not-to-scale sketch that specifies both the frequency and the decibels at every knee, and also as a proper plot on a semi-log paper attached. Do also that for the phase plot, and then find what is the magnitude in decibels and the phase in degrees of that transfer function at a frequency of 1 radians per second. Let's begin with the amplitude. I begin by identifying the knee on the decibels diagram. 1 at 5, there is a pole and a slope for a pole. And then there is a simple 0 at 20 and its contribution. And in this pair of complex conjugate poles, there is a knee frequency of 500 radians per second. The slope contribution is negative 40 decibels per decade. The entry on the decibels on the amplitude diagram, of course, because there is a 0 at 0, is 20 decibels per decade. Here it is. The entry curve has a slope of 20 decibels per decade because of this simple 0 at 0. At 5, this contribution flattens it out. At 20, it takes up again with this slope, and then this minus 40, turning it downwards with a final slope of negative 20 decibels per decade. The value of 1 radians per second, of course, is 20 log of 20 divided 5 divided 250,000, which is negative 95.92 decibels. From there, we compute the values at all the other knees. We need to compute these decades, those decades, and these decades up to 1 kiloradians per second. Now we have computed them. 0.7 decades from 1 to 5, 1.4 decades from 20 to 500, and 0.3 decades from 500 to 1000 radians per second. With the slopes and those decades and distances, we've computed A, B, and C, the climbs and drops, given down here, the 3 of them. With the value at 1, this one, we can compute all the others. Those values are minus 81.94 decibels, the value here, plus A, and adding B, we get negative 53.98 decibels here,
at the top and then downwards to 1000 radians per second, we subtract C and get negative 60 decibels, the value in decibels of the transfer function at 1000 radians per second. For the phase diagram, the first thing I do, because we found omega naught 500 radians per second for this pair of complex conjugate poles, is to find Z, 0.5 in this case. These are the 6 knee points. For 5, one at 0.5, another at 50. For this 0 at 20, one at 2, another at 200. And for this pair of complex conjugate poles, with the knee at 500 radians per second, one at 158 and another at 1581 radians per second. The slope contribution for this one is 90 divided by Z, 0.5. That is 180 degrees per decade. I mark now each one of the knee points, 0.5, 52, 200, 158 and 1581 on a scale with the contributions, of course. This one minus 45 degrees per decade and plus 45 degrees per decade, etc., etc. At 158 and 1581 for this pair of complex conjugate poles, the slope is 180 degrees per decade. Downwards on 158, because those are poles, and upwards on 1581 radians per second with the same slope. The entry is going to be 90 degrees because we have a simple 0 at 0, horizontal at 90 degrees. The slopes are entering with 90 degrees, minus 45 degrees per decade, horizontal, positive 45 degrees per decade, negative 135 degrees per decade, negative 180 degrees per decade, and horizontal after 1581 radians per second. Then we compute the decades with the slope. We have the drops. In this case, A is negative 27 degrees. The value here is 90. The value at this knee 2 is 6291 degrees. We do the same for all the others, 0.5, 0.1, 0.9 decades, and the corresponding drops or climbs B, C, D, B, C, and D appear down here. With those we compute the values at each knee. Here, 8539 degrees. In this one, 7157 degrees, and finally the exit value, negative 90.05 degrees. We were asked also to find what was the phase at 1000 radians per second. Down here, what is the value there? We just use the same technique. The distance from the nearest left knee, which is at 200 to 1000, is 0.7 decades. With a slope of negative 180 degrees per decade, we compute the drop, this drop, E, negative 125.81 degrees, starting at 71.57. The value here of the phase of the transfer function at 1000 radians per second is negative 54.25 degrees. That is the phase of the transfer function at that frequency. This is the approximate solution now on semi-log paper, the one we computed before, and as a reference I have plotted also the exact phase of that transfer function for each one of the frequencies of interest. However, this red curve was not part of the question in your exam, only the black segmented line. The exact amplitude of the transfer function versus the approximate one that we computed in blue can be seen here. In the circuit in figure 2, the switch A has been closed for a very long time and the switch B has been open for a very long time. That means that A is in steady state. The source is AC, the circuit is in AC steady state. But that is the previous question, question number 2. At t equals 0, this switch opens and this switch closes. Use Laplace methods to find and write, first in the Laplace domain and then part B as a function of time for t after the switches operate. What is the voltage in the capacitor? What is this voltage here? And when you have that, plot that voltage in the capacitor between t equals 0 and t equal half a millisecond. To do that, we need the initial conditions. We need to know what was the current in the inductor at t equals 0 minus before the switch is operated, and what was the initial voltage in this capacitor. But we computed those values in question 2, in the previous question of this exam. 1064 amps flowing like that, and 2816 volts with this polarity. We can draw the circuit for t greater than 0 with the switches operated. This one is open, eliminating the source from the circuit, and this closes this one into a short. We're left with this part of the circuit. Let's draw that in the Laplace domain. This is the way the circuit looks right now. This is the 4 ohm resistor over here. This is this 3 ohm resistor, and this is this 3 ohm resistor up here. This inductor, 10 millihenries, will be represented as an impedance S times L. Like that. Observe that instead of saying I multiply 0.01 times S, I prefer to write that as integer numbers for the sake of the calculator. And this impedance is 1 over SC. But using 833 microfarads, that can be written as 1200 divided by S. Again, using integer numbers. What about those initial condition sources? Well, they have the polarities of the initial conditions. So this is like that, and this one has this polarity, same as the initial conditions. The value of this one is L IL naught. This is IL naught, and this is L. 1064 I write as 1064 divided by 100 multiplied by 100th of a Henry. That is 1064 divided by 10,000. And this one, this is VC naught, this voltage, divided by S. But this is 2816 divided by 100. So 2816 divided by 100 S. And this is the circuit we need to solve. Let me use nodal analysis, M&A. I'm choosing this as my reference node. This is node number 1, and these are branch currents chosen arbitrarily like so. I write a KCL equation for node number 1. Currents going in, this one, that would be minus the source minus V1 divided by this impedance, that is the current entering node number 1. And that is equal to the current in this branch, V1 over 3, V1 over 3, plus the current in this one, which is V1 plus the value of this source plus 3 divided by this impedance. Like so. We have an equation, and we can find V1 in the Laplace domain. Let's do that. I have entered the equation but using x instead of the Laplace domain variable s, and I am about to solve for V1, linear solver. That is V1 in the Laplace domain. Let me copy that down. V1 is negative 751 divided by 25s plus 8750. But that is not the voltage we want. That is just the voltage of this node with respect to the reference. The voltage we need is the voltage in the capacitor. This voltage from here to there, that is the voltage in the capacitor. That is the voltage in this capacitor, this one. How do I find that? I use a voltage divider. Yes, that is a possibility, right? So I find the voltage here and then I subtract this one, but that is complicated, right? How about if I just find this current and then subtract this voltage minus 3 times that current, that is minus this drop, and that gives me the voltage in the capacitor, and that is what I'm about to do. Let me find this current, which is this term over here. That is that current. Let me compute that in the calculator. Let me do it by parts. That's V1. Let me add 2816 divided by 100s. 2816 divided by 100 times s, which is x in our combination. Enter, and I add those two values together. But that one at the top is a value I'm going to be using several times. So let me pick that, enter, so I have a copy of that V1 over there. I add these two together, and then I'm going to divide that by, let me create another expression. Let me divide that by 3 plus 1200 divided by s, which is x in our case. That one, divide. That is the current. But that current looks convoluted, so I ask eval to simplify that. That is the current in the capacitor. If I multiply that current times this resistor and subtract that from V1, I should get VC. That current, enter 3, multiply, subtract from V1, which is at the top, subtract, evaluate. That is the voltage in the capacitor in the Laplace domain. Let me copy that. And that is a solution to part A, the voltage in the capacitor in the Laplace domain. Let's find that voltage as a function of time, which is a solution to part B. I go to the calculator, mode, CIS, make sure that all the flags are cleared. OK. Make sure that x is a Laplace variable. It is. And I ask for the inverse Laplace. This is the voltage in the capacitor as a function of time. In this case, x is t, the independent variable. It is the sum of two exponentials. Let me copy them down. That is the voltage in the capacitor as a function of time, the solution to part B of the question. We still need to plot this one as a function of time between t equals 0 and t equals half a millisecond. Let's do that. To do that, let me push the down arrow, and in there I go red, copy, enter, and I go here to the 2D, 3D menu. Push and hold the shift key, and in here go to equation, edit, and red and paste. Enter and enter again, and now we go to the Windows one. Push and hold the shift key, Windows, and in here I say I want to plot that between 0 and 0.0005, half a millisecond, right? And the vertical axis, I don't know, automatic compute what you need, erase what you have, plot. That is the voltage we're looking for. That is the voltage in the capacitor as a function of time between 0 and half a millisecond. We need to find what are values there. Yeah, of course you do. Well, let's find what is the minimum value in the capacitor, and we'll say the minimum value in the capacitor is negative 28.2 volts, and that happens at 0.177 milliseconds right here. And that is the solution to this exercise. We copy that to the page the best way we can by hand, and we are finished. Thank you very much.
In the circuit of figure 3 below, this one, a sinusoidal source on the left is connected to a factory represented by this box on the right by a feeder, which is a cable represented by its resistance and its inductive reactance. The voltage at the source reads 140 volts. Let me write it down. The voltmeter at the factory reads 115 volts. These are RMS, of course. A water-damaged and partially destroyed tag for the feeder reads X is 5R, but the value of R is erased beyond recognition. That is, we do not know the value of this resistance, but we know that this reactance is 5 times that value, whatever that value is. An ammeter at the factory reads 33 amps. Oh, so we know that this current is 33 amps. A wattmeter at the source reads 3 kilowatts. Well, we know that the power here is 3 kilowatts, the power delivered by this source. The question is, what is the power factor and the load at the factory, including if that power factor is inductive or if it's capacitive? And also, what is the active power and the reactive power at the factory? And then, what percentage of the active power delivered by the source, those 3 kilowatts, is lost as feeder heat losses here? We shall see. I draw the phasor diagram where I write down the phasors I know. 115 volts, the voltage at the factory, 140 volts, the voltage at the source, and the current of 33 amps. You say, wait a minute, are you assuming the load is inductive? Well, that is a reasonable assumption. After all, the voltage drop from 140 to 115 is so significant that most likely the load is inductive. All right. What is what we need to find here? We need to find the power factor and the factory and the load. We need to find the angle between this voltage and this current and then take its cosine. What we need is to find this angle. Let me extend this a little bit. This angle is the angle I need to find. The power factor angle at the factory. How do we find that? Well, I don't know. Let's see what we know. And the source, we know the voltage. We know the power. We know the current, which is also 33 amps. Hey, we know the power factor here, don't we? Remember that the power and the source, PS, is voltage at the source, which is 140, times current at the source, which is 33 amps, times the power factor at the source. We know this is 3000 watts, this is 140, and this is 33. We can find this angle.
Let's find that angle. Let's say theta s is the arccosine of 3000 divided by 140, that multiplies 33. That's 49.51 degrees. What angle is that? This angle, this one, between the voltage here at the source and the current, which is coming in the circuit. This is the angle theta s, which we know it's 49.5 degrees. Holy. But what we need is theta f, that's right. And this is the one we know, that's correct. If only we knew this angle. Yes, what angle is that? Little delta. That is a torque angle. How am I going to find that? Well, we remember those two voltages and that angle are part of a triangle. This triangle. If we solve that triangle, we find delta, and then we can, yes. How do we find a triangle? If we know any three elements of the triangle, but not the three angles, we can solve the triangle. Let's see what we know. We know 115 and 140, two sides. We need delta, that's right. Can we find perhaps this angle? What angle is that? That is alpha, right. How? Well, there is a little triangle here, the cable triangle. Let's draw it. Like so. We can find what angle is this one. Absolutely. That is phi. That is the cable angle. What angle is that? Oh, that is the arctangent of who? X over r. But we don't know r. Do we care? X over r is 5. That's right. We know that angle. 78.64 degrees. That's right. This is this angle. To find alpha, we only have to subtract 5 minus this angle here. What angle is that? This one. Theta f. Oh, no. But that is the one we're trying to find. So, bummer. We cannot find alpha. We're left with only one. What about if we find this side of the triangle? This side is the voltage in the cable. Well, but for that we need the current, which we have, and we need the impedance of the cable that we don't. Bummer. So much for that. What about if we compute this angle here, the angle that we called beta? Can we? Oh, yes we can. We draw this line that is parallel to the current. Let's specify that's parallel to this one. Why? Because this angle here is known. Is it? Yes. This angle is this angle. The power factor angle of the source. We know that. We know that that is 49.51 degrees. And this one, this little one here, that is just 90 minus phi, and phi we know what it is. 1131 degrees. And then what? Well, check it out. This angle here is 90 degrees. It's a right angle. Is that right? Yeah, because this side is perpendicular to the current. That's why this is 90. So beta is 90 minus theta s minus 1131. That is right. Let's write it. Beta is 90 degrees minus theta s minus 1131. That 29.18 degrees. Bingo. Now we have three elements in our triangle. 115 volts on this side, 140 on this side, and this angle, which is 29.18. We can solve the triangle. We can use sine law several times until we find delta. That is what I'm about to do. Delta turned out to be 723 degrees. And we can subtract from theta f from theta s 49.51 minus 7.23. and obtain what is almost our answer. 42.28 degrees. The cosine of that is the power factor at the factory. Cosine of 42.28, which is 0.74. Inductive or lagging, depending on how you prefer to call that. And what else? Well, the power at the factory is voltage at the factory, which is 115, times the current at the factory, which is 33 amps, times that power factor, cosine of theta f, which is 0.74. You multiply all of that and you get 2.8 kilowatts. Actually, if you want to be picky, is 2,808 watts, if you want more digits, of course. And Q, the reactive power absorbed by the load, is 115.33 amps, and the sine of that angle that we just found, and that is 25.53 bars. That is approximately 2.55 kilobars. And the efficiency, well, let's see what the losses are. What the losses are. The power input by the source is 3,000 watts, but the power absorbed by the load on this side is less than that, is 2,808. So that means that the losses are 3,000 minus 2808, and that is 192 watts. In percentage, with respect to the 3,000 we're taking that from, that is divided 3,000 times 100%, that is 6.4%, and that is the answer to this question. Thank you very much.
This is the first and the last tutorial on body plots. This video is dedicated to the memory of the American mathematician from Wisconsin, Hendrik Wade Body. We start this tutorial with a quick review. A simple pole, a term like this one in the denominator of the transfer function, has a contribution to the amplitude plot like this, with a tail of negative 20 log A, up to the frequency A radians per second, where the contribution takes a dive with a rate of negative 20 decibels per decade, the slope. A squared simple term like this one contributes with a tail of negative 40 log A, up to the frequency A radians per second, then enters its slope with a decay rate of negative 40 decibels per decade. A pair of complex conjugate poles is announced by a term like this one in the denominator. Its contribution is exactly the same as that of a double pole at omega naught, this value. It does not depend on the damping factor. The contribution to the amplitude plot of zeros is the mirror image to that of poles across the 0 decibels line. After this brief review, let's get on with our tutorial. We are given a transfer function as a proper fraction of polynomials. Our first task is to find the roots of the numerator. We call those roots the zeros of the transfer function. Next, we find the roots of the denominator, which we call the poles of the transfer function. Let's find the zeros on the calculator. We enter the coefficients of the polynomial in the numerator as a vector. Issue the command to find polynomial roots, and the zeros of the transfer function are these: 1 real and 2 complex conjugates. This allows us to write the numerator as a product of factors. It is more useful to multiply the two terms of a complex conjugate root so we can see the undamped frequency omega naught and the damping factor represented by the Greek letter Z. But how? A graphical method is used to represent the complex roots on the complex plane, here and here. This distance from one root to the 0, 0 point will be omega naught. Given the real and imaginary parts of the roots, we use Pythagoras to find omega naught, 2.24 radians per second. Now, who is Z? The cosine of this angle, the angle between this distance line and the negative real axis. Z, the damping factor, is 2 over omega naught, 0.89. The numerator would look like this now. Now, let's find the poles on the calculator. We enter the coefficients of the polynomial in the denominator as a vector. Issue the command to find polynomial roots, and the poles of the transfer function are 4, 2 real ones and 2 complex conjugates. This allows us to write the denominator as a product of factors. It is more useful to multiply the two terms of a complex conjugate root so we can see the undamped frequency omega naught and the damping factor represented by the Greek letter Z. We use the same graphical method to represent the complex roots on the complex plane, here and there. This distance from one root to the 0, 0 point will be omega naught. Given the real and imaginary parts of the roots, we use Pythagoras to find omega naught, 8.06 radians per second. Now we determine Z. The cosine of this angle, the angle between this distance line and the negative real axis. Z, the damping factor, is 1 over omega naught, 0.12. The denominator can be written like this. All of this allows us to write the transfer function like this, where we identify the knee points of the amplitude body plot, a simple pole at 1, another simple pole at 8, and a double pole at 8.06 radians per second. Also, a simple 0 at 2, and a double 0 at 2.24 radians per second. Observe that I say double 0, double pole, and not complex conjugate pair, because for the amplitude plot, the contribution will not differ from that of a real double 0 or pole. Now, we sketch a draft plot, not to scale. On an axis, approximately equally spaced because this is not to scale, mark 1 tick per each 0 and 1 per each pole, and identify them with the frequency of each pole and 0 in the right order. Next, indicate the slope contribution at each pole and 0. At 1, there is a simple pole, so the contribution will be a slope of negative 20 decibels per decade. The same is true at pole 8. And a double complex pole at 8.06 that is negative 40 decibels per decade. A simple 0 at 2 contributes with a positive slope of 20 decibels per decade, and a double complex 0 at 2.24 radians per second plus 40 decibels per decade. We are almost ready, but we need to answer the question, what is the entry from the left? To answer this question properly, we need to ask another one. Is there any 0 or pole at 0 radians per second? If there are, how many? This transfer function, which is not our original one, has a simple 0 at 0, and the plot enters from the left, racing with a positive slope of 20 decibels per decade. This other transfer function, which is not our original one either, has a double 0 at 0, and the plot enters from the left, racing with a positive slope of 40 decibels per decade. This third transfer function has a simple pole at 0, and the plot enters from the left, descending with a negative slope of 20 decibels per decade. This fourth transfer function has a double pole at 0, and the plot enters from the left, descending with a negative slope of 40 decibels per decade. In our transfer function, there is no pole or a 0 at 0, so the plot enters from the left, horizontally, that is, with a slope 0 decibels per decade, up to the leftmost 0 or pole in our sketch, which is 1 in our function. And then what? What is the value of the curve at 1 radians per second? As long as there are no finite poles or zeros below 1 radian per second, which is a reasonable assumption as we saw in class, at omega 1 radians per second, the value of the entire plot is 20 log of this 0 times this other 0 squared, divided by this pole, and this one too, and finally this one squared. Oh, you say, but we saw it differently in class. Yes, you did this. Minus 20 log 1 plus 20 log 2 minus 20 log 8 plus 40 log 2.24 minus 40 log 8.06. Oh, but this is exactly the same as this. More, you could also compute that value as 20 log of 10 divided by 520. Try it. Let's compute it. So it enters horizontally with a value of minus 34.3 decibels until it hits the first knee at 1 radian per second. There, it takes a dive with a slope of negative 20 decibels per decade and stays that way until it arrives at the next knee point at 2 radians per second. The positive slope contribution cancels out the descent and makes the plot horizontal until it reaches 2.24. where it takes off at a rate of plus 40 decibels per decade up to the knee at 8, that subdues the ascent down to only positive 20 decibels per decade. We continue until 8.06, where the negative slope contribution forces the total curve to turn downwards with negative 20 decibels per decade. And that is the amplitude body plot of our transfer function. Now that we have the slopes, let's find out the decibels at each knee point. If we know the distance in decades between 1 and 2, which is log 2 over 1, we multiply that distance by the slope of the segment, minus 20 decibels per decade, to obtain the drop in decibels between 1 and 2. Again, for the segment between 2.24 and 8. Their horizontal distance in decades is log 8 divided by 2.24. Multiply that times the slope of 40 decibels per decade and you obtain the climb in decibels, and the same between 8 and 8.06. Let's compute the values. 0.3 decades between 1 and 2 at a slope of minus 20 decibels per decade. The drop is 6 decibels. So, the curve value at 1 is minus 34.3. The value at 2 is that minus 6. That is, minus 40.3 decibels. 0.52 decades between 2.24 and 8 at a slope of plus 40 decibels per decade climbs up by 21 decibels. So, we go from minus 40.3 up to minus 19.3 decibels at 8 radians per second. The same applies for the last segment. And this completes the sketch of the amplitude body plot for our transfer function. Observe that it drops as low as minus 40.3 decibels and climbs up to minus 19.2. That will fix the vertical scale in our semi-log paper drawing. This scale in decibels. Each of the knee frequencies is highlighted in red. Observe that the two rightmost ones, 8 and 8.06, are practically the same on the semi-log paper. I mark the vertical value obtained before at each knee point and draw the lines. Here, we have included one more decade to the right to see more clearly the exit of the plot. This also changes the vertical scale. If we superimpose the actual and exact amplitude plot, we can verify the accuracy of the approximate body plot for this transfer function. This big hump is created by the small damping factor of the complex pair of poles at 8.06. Now, a quick review of the phase contributions of poles and zeros. A term like this one in the denominator of the transfer function adds a contribution like this one. It introduces two knees, one decade below and one decade above. It goes from 0 to minus 90 degrees in 2 decades, so this slope is negative 45 degrees per decade. It is equivalent to this pair of infinite slopes that are easier to add, as we will see. A term like this one in the denominator introduces two knee points as well, also one decade below and one decade above, but it dives from 0 down to minus 180 degrees. That is a slope of negative 90 degrees per decade. It is equivalent to this pair of infinite slopes that are easier to add, as we will see. A quadratic term like this in the denominator of the h of s also introduces two knee points at omega 1 and omega 2, and they are equidistant to the undamped frequency omega naught. But how far from it? Omega 1 is less than a decade below omega naught, and omega 2 is less than a decade above omega naught. They are only z decades from omega naught. As it goes from 0 to minus 180, the slope also depends on z. It is minus 90 divided by z degrees per decade. Wait a minute, how do I compute omega 1 and omega 2? Omega 1 is omega naught divided by 10 to the z. Omega 2 is omega naught multiplied by 10 to the z. Same as in the other cases, it is equivalent to this pair of slopes, which are easier to add. One at omega 1, the other at omega 2, and with a slope of 90 divided by z degrees per decade. Once more, the contribution of zeros is the mirror image of the poles with respect to the 0 decibels axis. Before we move on to phase body plots, let me emphasize something. As we will talk of slopes in degrees per decade and vertical values in degrees, it is necessary to clarify what we mean before we begin. We are plotting the phase of the transfer function in degrees on this vertical axis between minus 100 degrees and 80 degrees versus the angular frequency omega of the input signal in radians per second. When I say degrees in what follows, I am not referring to the angle of the segment of the curve. Oh no, but to the vertical axis value of the curve at that point. The value of the curve here is 40 degrees. The slope of this segment of the curve is 100 degrees per decade, because it ascends at that rate on the vertical axis per advance on the horizontal axis. Let's establish for phase diagrams what is the entry value from the left. Phase plots always enter on the left and leave on the right as horizontal lines, but the question is, at what value in degrees? If there are no zeros and no poles at 0 radians per second as in our transfer function, the phase diagram enters as a horizontal line with a vertical value of 0 degrees. If there is a simple 0 at 0 as witnessed by this solitary s in the numerator, the phase diagram enters, again horizontally, but at a value of 90 degrees. There could be a double 0 at 0. See the s squared in the numerator? The phase enters as a horizontal at 180 degrees. Or perhaps there is a simple pole at 0. Note the single s in the denominator. The phase diagram enters at minus 90 degrees horizontally. Finally, if there is a double pole at 0, the diagram enters horizontally at minus 180 degrees. And that is the summary. Let's work on our exercise. Now we proceed with the phase diagram, the phase body plot in degrees versus radians per second. Each simple pole and each simple zero generates 2 knee points, 1 decade before and 1 decade after. For the simple pole at 1, the knees are at 0.1 and at 10. For the simple 0 at 2, the knees are at 0.2 and 20. For the simple pole at 8, the knees are at 0.8 and 80. For pairs of complex conjugate zeros or poles, they also contribute with 2 knee points, but only z decades before and z decades after. For the 0 at omega naught, 2.24 radians per second, the knees are at 2.24 times 10 to the negative 0.89, and 2.24 multiplied by 10 to the 0.89. For the pole at omega naught, 8.06, the knees are at 8.06 times 10 to the negative 0.12, and 8.06 times 10 to the positive 0.12. The numerical values are these. Again, we draft a not to scale rough diagram. On this axis, we mark 1 tick per knee, approximately equidistant. Remember, this is not to scale, and assign them to each one of the knee frequencies in the proper order. Now, the pole at 1 contributes with 2 slopes, one descending at 0.1 and the other ascending at 10 radians per second. The slopes are 45 degrees per decade because this is a simple pole. The pole at 8 contributes with 2 slopes, one descending at 0.8 and the other ascending at 80 radians per second. The slopes are 45 degrees per decade because this is also a simple pole. The complex conjugate poles at omega naught, 8.06, contribute with a descending slope at omega 1, 6.1, and an ascending slope at omega 2, 10.6 radians per second. The slope is 90 divided by 0.12, that is 750 degrees per decade. For the 0 at 2, slopes at 0.2 ascending, it is a 0, and at 20, descending at 45 degrees per decade. For the complex pair at omega naught, 2.24, slope at 0.29 ascending because these are zeros, and descending at 17.4. The slope is 90 divided by 0.89, that is 101 degrees per decade. We are ready to get the plot going. We enter it with a slope of 0 degrees per decade up to 0.1 radians per second. There, we descend at this rate, negative 45 degrees per decade, but only to 0.2 radians per second, where this positive 45 degrees per decade slope cancels out the descending one we were following, and the curve becomes horizontal, until, at 0.29, we had 101 degrees per decade. At 0.8, the slope abates by 45 degrees and becomes 56 degrees per decade. At 6.1, a brutal negative slope is added that pulls down our curve at a rate of negative 694 degrees per decade. But at 10, we had 45 degrees per decade, and our curve tones down its descent to a still steep negative 649 degrees per decade. I continue to do that until, at the end, the exit is, as predicted, horizontal. We have the slopes, but what are the vertical axis values associated with this phase plot? With the distance in decades between 0.1 and 0.2, and the slope, which we know to be negative 45 degrees per decade, we compute the actual drop in degrees, vertical axis, between this knee and this one. We can do the same with all other non-horizontal segments. Let's raise this curve to work better. We enter a 0 degrees vertical axis value because there is no zero or pole at 0 radians per second. The decade's distance between 0.1 and 0.2 is log of 0.2 divided by 0.1, that is 0.3 decades. Multiply that times the slope, negative 45, and get the actual drop between the first two knee points, 13.55 degrees. So, if the value at 0.1 was 0, then the value at 0.2 has to be negative 13.55 degrees. Let's do that once more for the segment between 0.29 and 0.8 radians per second. 0.44 decades. Slope 101 degrees per decade. Total climb 44.51 degrees. The value at 0.29 was negative 13.55. We add 44.51 and get the value at this knee point, which is 30.96. We do that for this and each one of the other segments and specify the value of the vertical axis at each vertex of the plot. The plot is thus determined. Plotting those values on semilog paper. And, superimposing the actual exact phase response curve, we see how close body's approximate diagram is. I have to emphasize that is so even in such a contrived transfer function. Before ending this session, let me bring to our attention an interesting quadratic term that appeared in a transfer function a few years back. A term like this one. And you say, what is that? And I say, 2 poles. And you say, right, 2 poles on the imaginary axis, one at J50 and another at negative J50. Indeed, a pair of complex conjugate poles. But what is omega naught? It is the square root of 2500. It is 50 radians per second. And the damping factor, the z? It is 0. By the way, the decibel contribution of this 0 damping complex pair remains the same, but its phase contribution looks like this. How do I include this phase contribution? Its slope is infinity. Draw the phase plot for all other zeros and poles, and then subtract 180 degrees at all frequencies above 50 radians per second. Yes, there is discontinuity. And with this, my invisible friends in the classroom and all over the planet, this is the end. Thank you very much.
Well, this is what you might call a raw video. It hasn't been edited. It's put together very quickly in response to the request of some of my students before the final exam. In this circuit, they tell us the circuit's been like that with this switch open for a very long time. That phrase has been like that for a very long time. Tells us that the circuit is in steady state. So we write steady state. Because the source is an AC source, the circuit is in AC steady state, and that implies that its solution can be done using phasors, and we will do that, phasors. But to use phasors, we represent the voltage source with a phasor, which would be 2 with 0 degrees as a phase, 2 with an angle of 0 degrees volts. The 2 remains the 2, the resistances remains the same, and then we need the frequency. Omega is 2 radians per second, as we see there, and from that 2 radians per second we can compute the impedance of the inductor and the impedance of the capacitor. That is the next step. Reactance of the inductor, omega L, 2 times 1 is 2 ohms. The reactance, right? The impedance is J times the reactance, would be J2 ohms. So we can write that in a moment. The reactance of the capacitor is a negative 1 over omega C, and that would be negative 1 over 2 radians times 1/6, and that is negative 3 ohms. So the impedance is negative J3. Let's draw this circuit in the phasors domain. Instead of this 1 Henry, we have its impedance, which is J2 ohms. Instead of the capacitor, we have its impedance, which is negative J3 ohms. Well, the question actually is, what is the voltage in the capacitor with this polarity V of C for t greater than 0? Well, what happens at t equals 0? At t equals 0, this switch closes. Or when it closes, it bypasses this resistor. It effectively removes that from the circuit. So we find what were the initial conditions in the circuit at t equals 0 minus when the circuit was still in AC steady state. We want to find what was the current in this inductor and what was this voltage in this capacitor. Let's solve the circuit when it was in AC steady state. So in the circuit in the phasor domain, we could find that current and this voltage using many different methods. We could use M&A, nodal analysis, that is, or we could use mesh analysis. But I'm going to solve this in a different and easy way. This current here is the current in the source. I will compute that current dividing this voltage of the source by the total impedance seen by the source. So let me write that. That current in the source, which is also the current in the inductor as a phasor, by the way, will be the voltage of the source, which is 2 with 0 degrees is just a real number, 2, divided by the total impedance, which is 2, 2. This is this impedance, plus the series of 5 in parallel with negative J3, plus 5 in parallel with negative J3. And that is that current. And we use a calculator to solve for that. So 2, which is the voltage, and then 2 space 2. That is that impedance. And then 5 enter in parallel with J03 negative. Want to put those two in parallel, go to next Z in parallel with Z and add that with the other one. That is the total impedance. Divide 2 by that. That is the current, but I want a numerical value. That is the current. That is the current in rectangular mode, but it's a current. I'd rather have that in polar form this way. 0.6 amps with a phase of radians? No, I want degrees. 3.54 degrees. To find the voltage in this capacitor is as simple as 2 volts minus the drop in this impedance. And that is how I'm going to compute that. The voltage in the capacitor is 2 volts minus the drop in that impedance, which is the value of that current IL that we just computed, this one, multiplied by the impedance 2 of this branch. And we do that in the calculator. And that is the current, all right? Let me duplicate that. That multiplies 2 space 2, but in rectangular mode. Multiply them. And then subtract from 2. I subtract that. And that is the voltage in the capacitor. But in rectangular mode, in polar form, is 155 volts with negative 55.49 degrees. Like so. And then what? Well, what we need is to find those voltage and currents, but not as phasors, but at exactly t equals 0. But before doing that, let's write those currents and voltages as functions of time. The current in the inductor as a function of time is the big value of 0.6 root 2 sine of 2t plus 354 degrees. 354. Convert that into radians, of course. And that is the current. If we evaluate that at t equals 0, we obtain the initial current in the inductor IL naught that we will use in the Laplace transform solution. The voltage in the capacitor is the peak value 155 root 2 sine of 2t minus 43 degrees, but in radians. Multiply pi divide 180, and those are volts. Evaluated at t equal to 0, we obtain VC naught, which is the other initial condition that we will need. So sine of 354 degrees multiplied by root 2 times 0.6, that is this value. That current, this one, pick, enter, and now we are in polar. Let me, from the complex number format to the stack, I want the sine of that. It's in degrees, yes, that's right. The sine multiply times 0.6 root 2 multiply, evaluate that as a number, and that is the value of the initial current in the inductor. Let's write that in milliamps. 52.52 milliamps. For the voltage we do something similar. Let me pick this value down here in degrees, and let's break that, and let's take the sine of that multiplied by 155 and by root 2, evaluate that as a number, and we get that the initial voltage in the capacitor was negative 1.8 volts. Well, what this means is that the initial voltage in the capacitor actually was not like this, but like that, 1.8 volts. So if I want to write it here, it's the same. Good. We are ready to go to the Laplace domain solution with this switch closed, which eliminates bypassing this resistor. Now we're going to represent the inductor with an initial condition source in series with an impedance, SL. Right. The initial condition is going to be L. IL naught is going to have in this polarity. L is 1 Henry and IL naught is 52 milliamps. Allow me to write it like this. So I use integer numbers, which is better for the calculator. For t greater than 0, we have only the 2 ohm resistor. The other one has been bypassed by the closed switch. And the capacitor is represented by its impedance, 1 over Cs, in series with an initial condition source with the polarity of the initial condition. This value is 1.8 divided by S. Well, let me write that as 18 divided by 10S. This source is a sinusoidal one with a peak value of 2 root 2, showing Laplace, and that is 2 root 2 omega, which is 2, that is 4 root 2, divided by S squared plus omega squared, S squared plus 2 squared, which is 4. That is the Laplace domain representation of the source. I think we're ready. This is just S, of course, because L is 1, and this is going to be 6 over S. We are ready to solve that circuit in the Laplace domain. I'll choose this as my reference node, and this is node number 1. What's the advantage of this choice? That when I find V1, V1 will be directly the voltage in the capacitor, which is this one. Please do not fall in the trap of believing that the voltage in the capacitor is the voltage in this impedance. No, because the capacitor is represented by these two elements, all right? So the voltage in the capacitor is from here to there, which in our case is V1. Well, let's solve it. Branch currents with the direction of your choice, and we write a KCL equation. KCL1 is the value of this source. Let me write it here. 4 root 2 divided by a squared plus 4 plus the value of this source, which is 52 divided by 100,000 minus V1 divided by the impedance of the branch, which is 2 plus S. 2 plus S. And that is equal to current that leaves the node, this one, V1 over 2. V1 over 2 plus the current in the capacitor, which is V1 plus the source divided by the impedance. So let's write V1 plus the source divided by the impedance, which is 6 over S. And that is the equation we're going to enter in the calculator. That is the equation. I'm using the letter X instead of V1 because it's easier to type. Let's solve it. Turn that into an array of only one equation. We put X in an array, and then we solve this equation for X. Symbolic solver, linear system of solution, and that is V1 in the Laplace domain. Let's copy that. But before that, so let me show you that the CIS in mode has all those little buttons unchecked. Good. So that's why it worked for me. And this would be the solution of the problem if we were being asked, find the voltage in the capacitor in the Laplace domain. Observe that instead of writing a longer expression, I represent this constant number A with this expression down here. Well, but we were asked to find that voltage as a function of time, so we need to find the inverse Laplace transform, and that is what I'm about to do. First things first, let me break that array objects to pieces, eliminate that count, and this object also break that into pieces, eliminate these two symbols. That is the expression I want to find the inverse Laplace transform of. But before doing that, I have to match this variable of the Laplace domain with the independent one that appears here. So right now, this wouldn't work. I have S here and I have X there. How do I change that? Mode, CIS, and this independent variable has to be S. Edit that. And then you can go there and say this variable is going to be S, okay? And okay. See, now it's S. Now when I ask for the inverse Laplace transform of this one, it will know that this is the independent variable. And that is what we're about to do. One directory up, variables, next one, Laplace directory. I want to find the inverse Laplace transform. I prefer to solve an equation or to find its inverse Laplace transform with the system working in radians and in rectangular mode. Let me go for that. Inverse Laplace. There is the solution. That is the inverse Laplace transform of that voltage. So this is the voltage as a function of time. You're saying, but there is an S here. Yes, in the time domain, the independent variable is time. So for the calculator, S is t, is the time. It has an exponential, decaying exponential. 5 over 2 times t, multiplying a cosine of this frequency times t, times a constant. You say, well, I cannot read that properly. If I go down arrow, I see that there, and that is not that good either. Yeah, down, 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 until it becomes a transparent block, and then I travel through my expression, copying each one of the values to my paper. I can do that. I simplify that with wait, and I get an expression there. With what flux did I do that? Let's see. only the approximate one. All the others remain cleared. Okay? Well, that expression is the one that I'm going to plot. And down arrow, red, copy, enter. In 3D, down here, edit, red, paste, bingo, enter, and the variable, independent variable is S. Do not forget to change that to S. I had already done it. And now we go to Shift Windows and say I want to plot that between 0 and I don't know, 10 is good. And what is the vertical axis? We'll make a computation there. Good. Erase what you have and draw a new plot. That is the voltage in the capacitor. It begins at negative 1.8 volts and then it moves to a different oscillation, the new steady state. If this circuit is in steady state after 5 taus, what tau? Well, this tau, 1 over 2.5. In that time, 5 times that, 1 over 2.5, the circuit is again in AC steady state. Thank you very much.
A real coil has a resistance R and an inductance L. The coil is represented by a model. The model consists of its resistance R in series with its inductance L. To determine those values R and L, the coil is connected in series with an external resistor Rx of 10 ohms. Then we apply a sinusoidal voltage of 60 Hz, 36 volts, to the entire group coil plus Rx. We measure the voltage of the coil, 22.4 volts, and we also measure the voltage of the external resistor, 20 volts. Calculate the values of R and L, the resistance and the inductance of the coil. So this is the situation. An external resistor Rx of 10 ohms in series with the coil that is represented by its resistance R and its inductance L in series. We apply an external voltage between these 2 points, right? This voltage of 36 volts. When we do that, there's going to be a current flowing through that branch. That current is unspecified. I'm going to call that current I. But one thing is true, it's going to be the same current through the external resistor Rx and through the coil. That current will produce a voltage drop in this resistor and a voltage drop in the coil as well. And we know those voltages. We know that the voltage in the external resistor is 20 volts. This is 20 volts, and we know that the voltage in the external coil, this one, is 22.4 volts. So we have 3 voltages, and we know that according to KVL, Kirchhoff's voltage law, the sum of these 2 voltages, the voltage in the coil and the voltage in Rx, have to be 36 volts. In the phasor problem, we're going to choose a phase reference. In this case, I will say the reference for phases is the phase of the common current I. So this current is assumed to have 0 degrees for a phase. Well, the voltage in Rx is going to have the same phase, 0. That's going to be our current. The voltage drop in this resistor is going to be in phase with that current. So this is the voltage in this resistor, voltage in Rx. I'm going to write there 20 volts. Good. And the voltage in this resistive part of the coil, V in R of L, is going to be also in phase with that one, and is in series with the other voltage. So this is the voltage in the resistance of the coil. And the voltage, this one, in the inductance of the coil is going to be at 90 degrees, leading the current. This is going to be the voltage in the inductive part of the coil. If we add together these two voltages, this one has to be the voltage in the coil. If we add together the three voltages, this one, that is the entire voltage of the group. So we know this is 36 volts, and we know that this is 22.4 volts. Of course, we can use cosine law to find this angle theta, and subtracting that from 180 degrees, we find out this angle alpha. VR is going to be 22.4 cosine of alpha, and VL is going to be 22.4 sine of alpha. And then we say, well, those voltages, VR and VL and 20 volts, all of them are proportional according to Ohm's law to Rx and I, to R and I, and to L and I. So you see how we can use proportionality to find the values of R and L? Let's do it. I'm using cosine law to find this angle theta, 116.10 degrees, and alpha is 180 minus theta, 63.90 degrees. This voltage VR in the resistance of the coil is going to be 22.4 cosine of alpha, and that is 986 volts. And the voltage in the inductive part of the coil, this one, is 22.4 sine of alpha, 20.12 volts. From this resistor of 10 ohms with 20 volts, we compute the current. The current is 20 volts divided by 10 ohms. This is a current of 2 amps, of course. But we know what is the voltage in R. It's 986 volts, and we know the current is 2 amps. We can use Ohm's law to find what is R. That resistance is 986 volts divided by 2 amps for 93 ohms. For the inductive part of that coil, according to Ohm's law, that voltage 2012 is the product of X of that coil that multiplies the current of 2 amps. So we can find what is the reactance of that coil. It's 2012 divided by 2, 1006 ohms. But the reactance of an inductance is 2 pi F times L, like so, which means that the inductance can be obtained directly as 1006 divided by 2 pi 60, which is approximately 377. That is 2668 millihenries. And that is the answer of this problem. Thank you very much. In the parallel circuit of figure 1 below, the RMS values of the three currents I1, I2, and IT are 18 amps, 15 amps, and 30 amps correspondingly. Determine the values of resistance R and of the reactance XL. In every phasor problem, we choose one voltage or one current as the reference for angles, as the 0 degrees phasor. In this case, I'm going to choose this voltage as the 0 degrees phasor. That means that that voltage has 0 degrees. The current in this resistor, this one, I'm going to call that IR, has also 0 degrees because it has to be in phase with that voltage. The current in this resistor, which is I2, has also 0 degrees for the same reason. And the current in this reactor, which I will call IX, is at 90 degrees behind this one, so it has a phase of negative 90 degrees. So we can draw a phasor diagram readily. This would be the voltage phasor with its 0 degrees. This is the current I2, this one, in phase with the voltage, because this is a resistor, 15 amps with 0 degrees. we have to add to this current also the current IR, which is also in phase with the voltage. It also has 0 degrees. So this one is the current in IR. It's unknown so far, IR. And to those two currents we have to add a third current, IX, which is lagging 90 degrees behind the voltage. So that current in that reactor is this one. This is IX. And then we know that if we add together those two, IR plus IX, I gotta get 18 amps. Like so. And if I add together the three of those currents, I gotta get the total current, which is 30 amps. Like so. From this diagram, of course, we can compute what are the values IR in these resistors, this current, and the current in the reactor, IX. How? This angle here, theta, we find using cosine law, and then subtracting that from 180 degrees, we get the angle alpha. 18 times cosine of alpha is IR. 18 times sine of alpha will be IX. So that way we investigate what are the values of currents in R and in XL. We also know the voltage in those two elements, which is V, and V is no other than 15 amps times 460 volts, 0 degrees is the value of the voltage in each one of the three elements. If we find those currents, we use Ohm's law to find R and to find XL. Let's do that. This voltage, I repeat, is 4 ohms times 15 amps, that is 60 volts. 0 degrees, our convention. Now let's go to this triangle using cosine law. In this angle here, the value of theta is 130 degrees and some change, and the value of the angle alpha is 49.46 degrees. We are ready to compute IR and IX. These are the values of currents in the resistor, 11.70 amps, and in the reactor, 13.68 amps. If we divide the voltage 60 by each one of those currents, we obtain readily R and XL. R is 60 volts, 0 degrees, which is a real number, divided by the current 11.70, which is also a real number. It has a phase of 0 degrees, as we see that there. And that is the resistance we're looking for, 5.13 ohms, this resistance. Let's find the reactance XL. That reactance is just 60 volts divided by the magnitude of the current through that reactor, which we found is 13.68 amps, 4.39 ohms. If you're thinking, well, wait a minute, you're dividing real numbers to find their reactance. Should you not using Ohm's law with complex numbers? Should this V voltage, shouldn't be that a complex number V? Well, it is. It's 60 volts with 0 degrees, which is a real number. But you say, and the impedance of this one should be JXL. By all means, let's do it that way. We say, well, the impedance JXL would be the voltage 60, we know that is a real number, divided by the current. By this current here, and that current has a value of 1368 amps with an angle of negative 90 degrees. Negative 90 degrees. When you perform the operation, what you get is J times the reactant that you obtain. You see what I did before was just dividing the absolute value of the voltage by the absolute value of the current, and that would have given me the absolute value of the impedance, which is no other than the reactance directly. And those are the results of this problem. Thank you very much. The circuit in figure 2 is energized by three sinusoidal voltage sources, VA, VB, and VC. The values of those sources are given up here. VA is 3 root 2 sine 400t plus 10 degrees. Those are in volts. And VB is 3 root 2 sine 400t, 0 degrees. And VC, 5 root 2 sine 400t with negative 20 degrees. The question is, part A, find the current in each source as a function of time. Current here, current there, and current there. We begin by representing those sources as phasors. 3 with 10 degrees, 3 with 0 degrees, and 5 with negative 20 degrees. And now we're going to represent every reactive element, that is every inductor and every capacitor in the circuit, with its impedance. To determine the impedance, we need the angular frequency of the sources, which is given 400 radians per second. That is omega, 400. So we utilize the formula for impedance of an inductor, which is J omega L. Omega in this case is 400, and L is the value of each one of those inductors. And the impedance for a capacitor, which is negative J 1 over omega C. Let's do that for each one of the reactive components. For the 5 millihenries inductor, the impedance is J2 ohms. The impedance for the 10 millihenries inductor is J4, the impedance for the 15 millihenries inductor is J6, and the impedance for the 20 millihenries inductor is J8 ohms. The impedance of the 500 microfarad capacitor is negative J5 ohms, and the impedance of the 250 microfarads capacitor is negative J10 ohms. And now let's represent the circuit with impedances and phasors. First, the voltage phasors for the three sources. Now the impedances. We're going to write this as 2, 2, 2, negative 5, 3, 6, 2, 4, 20, 0, negative 10, and 0, 8. For convenience, in rectangular form, the impedance of each one of the branches. Like so. Now we are ready to write equations. For that, we use M&A. Choose a reference node, this one will do, and label this as node 1 and node 2. Next, the branch currents are chosen arbitrarily like so. And after that, we immediately realize there is no controlling the source, so no controlling equation, there is no evil branch, and all we're left with is only two KCL equations. Let's write those two KCL equations, one for this node 1 and one for node 2. Currents entering the node, there are two, this one and that one. Currents leaving the node, there are two as well, 4 terms. This current is VA minus V1 over 2, 2. VA minus V1 over 2, 2. Plus the current entering through this branch, that is V2 minus V1 plus 3. V2 minus V1 plus 3, which is VB. Let me write VB divided by the impedance of the branch, which is 2, 4. And that is equal to the currents leaving the branch. This current on the vertical branch is V1 divided by 2, negative 5. V1 divided 2, negative 5, plus this other current, which is V1 minus V2 divided 3, 6. Good. Let's write KCL 2. KCL for node number 2. There are 1, 2, 3, 4, 5 branches connected to that. We have 5 terms. Currents arriving in the node, this one and that one, and all the other 3 currents are leaving the node. So let's begin with this one. V1 minus V2 divided 3, 6. V1 minus V2 divided 3, 6. Plus this current here, which is VC minus V2 divided 0.8 equal to the current on this 20 ohm resistor, V2 over 20, plus the current in this capacitor, V2 divided by 0, negative 10, plus the current on the top branch, which is, as we saw before, V2 minus V1 plus VB. V2 minus V1 plus VB divided by the impedance of the branch, 2, 4. Those are the two equations, and the two unknowns are V1 and V2. Let's enter them in the calculator and solve for them. 3, enter 10 degrees, so that is the first one. And the other one is just 3 volts, and the last one is 5, enter 20 negative. That is, those are the three ones. What I'm going to do is store those in those three variables, D, E, and F. The first one is stored, green F, and green E, and green D. Now we have the values of VA, VB, and VC stored in those three variables, D, E, and F, which will simplify our typing of the equations. Equation writer. These are the two equations. Observe that D, E, and F appear explicitly in lieu of VA, VB, and VC. Here they are. Those are global variables. We stored the voltages of the sources in. Check out. This is VA, this is VB, and this is VC. Excellent. And now let's declare a system of two equations with two unknowns. This way. And we're going to ask for the solution of the two unknowns, V1 and V2. Invoke the symbolic solver, linear solution, and those are the answers. And immediately you realize, hey, wait a minute, those solutions are given in terms of D, E, and F. I want to evaluate that expression so the substitution is complete. But before doing that, let's break this system into its components. This way, break the object into pieces, eliminate the countdown here, and now we evaluate each one of those separately. Eval, swap, eval the other one. Those are the two voltages we were looking for. V1 is 3.624 volts RMS with a phase of negative 42.449 degrees. V2 is given above. Now that we have those two voltages, V1 and V2 with respect to the reference node, we can compute the current in the source A, this IA, the current in B, and the current in C in each one of the sources. Those three currents happen to be given in the equations already. This is IA, and this is IB, and this is IC. We substitute those two values, and they are obtained readily, IA, IB, and IC. We begin with IA. VA minus V1 over 2. VA is stored in D, so D minus V1, which we pick from the stack, pick, enter, and we're ready. We subtract them and divide by round percentages 2 space 2, and that is a current divide. You say, hey, what monstrosity is that? Well, let's eliminate the left-hand side with clear equation, and that is the current IA, 1.054 amps with a phase of 39.596 degrees. That is IA. But the exercise is asking us to write that current as a function of time, so we use the RMS value and the phase this way. The phase on one side and the function of time on the other, RMS value times root 2 omega t, and the degrees times pi divided 180 to convert them into radians. And we do the same for the current in IB, this one, and for the current IC, this one. And those are the three currents in the three sources, which is a solution of part A of this exercise. In part B, we're asked to find what is the voltage in each one of the capacitors. So the voltage in this capacitor is directly V2, which is known now. As a function of time, you know you only have to use this RMS value of V2 times root 2, the frequencies for 100 radians per second, and convert these degrees into radians. The same way, you know how to do that. And this voltage in this capacitor, this one here. Well, you know V1, and you use a voltage divider between this 2 ohm resistor and this negative J5 reactor. That way you obtain that. That would be this voltage is V1 multiplied by negative J5 divided by 2 minus J5, and that would be the voltage here. As a phasor, you can convert that as a function of time. What about the last? Just multiply the voltage times the complex conjugate of each one of the currents and represent them in rectangular form, which is straightforward. Thank you very much. A 400-volt three-phase voltage source, this one, is feeding a three-phase load, this one, through three line wires, those three over there. The source is supplying 55.6 kilowatts at a power factor of 0.66 inductive. Of course, this is three-phase power. We know what is the power here and the source. Total three-phase power at the source 55.6 kilowatt at a power factor 0.669 inductive or lagging, which is the same thing. The load is absorbing 53 kilowatts at a power factor of 0.707 inductive. Well, that is, of course, the total three-phase power absorbed by the load is 53 kilowatts at a power factor of 0.707 inductive or lagging, which is the same story. The first question is, what is the voltage on the load? We know that the voltage here, the line-to-line voltage, is 480. What is this voltage here? What is the voltage and the load? Well, let's see. We know the total three-phase power at the factory, which would be root 3 times V line, and this one, times I line, and this current here, times the power factor, which is 0.707. And that has to be this value here. You say, oh, I know everything, this is what I want to know, but I don't know the current in the line. Bummer. Let's see how I can compute the current in that line. Let me turn our attention to the source. Well, in here, the total three-phase power at the source is root 3 times V line, which is this one, which is 480 volts is given, and it's known. 480, that multiplies the current in the line, this one, which is unknown, and multiplies the power factor on the source, which is 0.669. So from this equation, because this is just this total three-phase power, we can obtain the current in the line, like so. 100 amps. That is the current in the line. With that current in here, we obtain that the voltage, VL, and the factory, this one, is 433 volts. The line-to-line voltage at the source, 433 volts. That takes care of part A of the exam. Now let's work on part C. Observe I'm jumping from part A to part C because it's simpler than part B. If the load is a triangle of impedances and each one of those three impedances is a resistor in parallel with an inductive reactor, what is the value of such resistor and such inductive reactor in ohms? Before proceeding, let me erase all of this. Let me begin by assuming that this load actually is connected in a Y, like so, with three equally sized impedances connected like this. The voltage here we determined was 433 volts. That means that this voltage here is 433 divided by root 3. And the current here is 100 amps. We obtained that before, so we can compute the value of this impedance. That impedance, its magnitude is 2.5 ohms. If those 2.5 ohms can be represented as a resistor in series with an inductor, those 2.5 ohms would have the same angle that is dictated by the power factor, which is R cosine of 0.707, which is 45 degrees. So we know now what should be the value of R in series and Jx in series.
Each one of them has the same value according to the angle, and it's 2.5 cosine of 45 and 2.5 sine of 45 degrees. 1768 ohms, and this is J1768 ohms. But what we want is to represent each one of them in a delta. Well, a delta. Yeah, so let me roll the screen a little bit down. And we say, if this represented as a delta would be three impedances like this, and like this. Well, those impedances have the values of these ones multiplied times 3. I just multiply them times 3 and write them here. That is 5.303 ohms and J 5.303 ohms, and the same is true for each one of the other phases of that delta. But now we want to represent this as a parallel of a resistor and an inductor, and we've done that before. We did that in the quiz. Represent them, each one of those in the delta, by this R in parallel with this JXP. You do exactly what you did in your assignment or homework, and you get 10.61 ohms here, and this one has the value of 10.61 ohms as well. Now finally, let's go for part B. What are the resistance R, this R, and the reactance X of the cable at each one of the three lines between the source and the load? For that, allow me to represent only one of the phases of this system, assuming that they are Y, Y, and Y, Y. So here's one of the phases of the Y-connected source, and now we have the reactance and the resistance of the cable and one of the Y-connected loads. Excellent. Let me write in RJX, and this value, this source, is actually 480 divided by root 3 volts. And this one, that is 433 volts divided by root 3 volts. By the way, this is 277 volts, and this is 250 volts. That's what it is. And the current is also known. The current we computed, that is 100 amps. And we know the power factor here, which is 0.707 lagging, and we know the power factor here, which is 0.669 lagging as well. Let me move the screen a little bit further down so we have room to work with. A phasor diagram for that. The voltage at the factory is 250 volts. Then the voltage at the source, 277 volts. This is the drop, V in drop, and the cable, which has, of course, a resistive part and a reactive part. We know this is Ri. We know this in size is Xi, right? Its magnitude. And we know that V drop, its magnitude, is I multiplied by the total impedance, which is R squared plus X squared. Good. The current is parallel to this side. The current is like so. The current is 100 amps. This angle is known. The angle is known. The angle is 45 degrees. It's the I cosine of 0.707. This is 45 degrees. And this angle here is known. It's the power factor angle at the source, which is the R cosine of 0.669 inductive. So this angle is 48 degrees. That means that this little angle that we call delta is 3 degrees. 3 degrees only. So now we have a triangle in which we know this side, this angle, and this side. We solve then using cosine law. We find VDR. That voltage is 30.5 volts, approximately this one. But that voltage is just the total impedance, and that is just 100 amps multiplied by the absolute value of the impedance, which is given by this square root. From that, the absolute value of the impedance is just 3047 divided by 100, which means that this angle here is 180 minus 151.5 plus 45 degrees. That gives me the angle of the impedance of the cable, which is 73.53. degrees. Moving the screen a little bit further down, we know then that R is Z times the cosine of this one, 0.305 cosine of this angle here, and X is 0.305 sine of that angle there. 86.4 milliohms for the resistance of the cable and 0.292 ohms for the reactance of the cable. And that is the solution to part B of this exam. Thank you very much.
This is the exercise we need to solve. It's a circuit with two sources, a current source, 4u of t, and an exponential voltage source, 2 exponential of negative tu of t. One capacitor, one inductor, and two resistors, all of them with a value of 1. What is the question? Find this current. What current? I don't see any current. This current. The current in the inductor flowing from left to right. I naught. Find that current first in the Laplace domain, that's part A of the question, and then once you have that, find that current in the time domain. And once you have that, I naught in t, then plot it. And also at t equals 1 second, find what is the value of that current. Let's begin. We begin finding the initial conditions of the circuit, that is, the initial current in the inductor and the initial voltage in the capacitor. We look at the circuit as it was right before the activity began, at t equals 0 minus. But we realize that at 0 minus, this source multiplied by u of t's value was 0. And the same was true for this current source down here. Both were 0 for t equals 0 minus. That means the initial conditions were 0. They were like that for a long time. 0 volts, 0 amps. What does it mean? It means that IL naught, the initial current in the inductor, was 0, and VC naught, the initial voltage in this capacitor, was 0. When we draw that circuit in the Laplace domain, the IC sources will not be there. They are at 0. Let's go to the Laplace domain. We'll replace the reactive elements by their impedances. This inductor becomes S, its impedance, this capacitor 1 over S. The resistors keep their values, 1 and 1 ohms. Now this 4u of t becomes in the Laplace domain 4 over s, and this exponential function of time becomes in the Laplace domain 2 divided by s plus 1. We are ready. Let me do that in a prettier way, like so. Now to solve that circuit for the current that we need in that inductor, let me choose a reference node, this one, and identify nodes 1, 2, and 3. Next, we highlight the branch currents beginning with the ones we need to find this one, I naught. And also, if we notice that there is an evil branch on the top of the circuit, let's also give a name to that evil current, IV, the evil current in that evil branch. For the other branches, currents are chosen arbitrarily, of course, and we begin by writing equations. M and A. The first question, is there any controlling variable? No, none in this circuit. Any evil branch? Yes, the one we observe at the top of the circuit, this one, that says that V3 is higher than V1 by the value of this source, and that is the evil equation number 1. This equation, V3 minus V1 equals to the value of the source. Next, we write a KCL equation for each one of the nodes. For KCL 1, we have currents going in I naught, currents leaving the node IV, and this current, which is V1 divided by 1 ohm, V1. Observe I keep using the labels I've chosen for my variables I naught and IV. Next, KCL 2. currents going into node 2, 4 over S, this one, leaving that node on the right I naught, and on the left, V2 minus V3 divided by the impedance 1 over S. That means S that multiplies V2 minus V3. And last, KCL for node number 3, 2 currents arriving there. IV, the evil current on the top, this one, and the current between nodes 2 and 3, V2 minus V3 times that S. That is equal to the current in this 1 ohm resistor V3 divided by 1 ohm V3. We have 4 equations, but if we count, we have I naught, IV, V1, V2, and V3. We have 5 unknowns and only 4 equations. We need one more equation. Why so many unknowns? Because I chose to give a name to this current instead of saying that I naught was V2 minus V1 divided by S. Let's add that equation. That's going to be our extra equation. I naught is defined as V2 minus V1 divided by S. We have now 5 equations and 5 unknowns. Let's go to the calculator. We begin by entering the equations, this one, and this one, and this, and that, and the other. And then we make an array with programs, type, make me an array with 5 equations, like so. Next, we specify the unknowns we want to solve for. We invoke the symbolic solver, ask for a linear solution, but before doing that, I always go to Mode and to CAS and check there that first, the variable x, the independent variable, coincides with the one I'm using for the Laplace domain representation of S, and also that all those radio buttons are unchecked. Here I need to uncheck this one. Check, it's clear. And then OK, and I'm ready to ask for a linear system solution. And this I naught is the current we're looking for. And this was the solution to part A, the current in the inductor in the Laplace domain. To find that current in the time domain, we go to the calculator. To obtain the inverse Laplace transform of this one, the first thing I do is I break these systems of solutions into pieces. I go to Programs, Type, make that object into pieces. There are 5 of them. This one is the one I want to process. But this is also an object with several parts. Let's break that also into pieces and eliminate the count and the equal sign that we don't care for. This is the expression I want to take back from the Laplace domain to the time domain. I check again that x and x coincide, that in mode CAS all the flags are clear, and then we proceed. I have assigned the inverse Laplace transform call to this key, but in your case you may do so or just go to the directory and find it. Inverse Laplace transform of that. This is the current in the inductor as a function of time. The independent variable x in this case represents time. And this is the current in that inductor I naught of t as a function of time. That is the solution to part B of the exercise. Observe it's a constant minus a decaying exponential and an oscillation of frequency 1 radians per second. Next, we plot that as a function of time. For that, let's also go to the calculator. To plot that expression, the first thing I do is the down arrow key. I enter the equation writer. In there, redshift and copy. So I have a copy of that expression in the buffer of the calculator. Enter to get out of there. Now to the plot dialog. Press and hold this shift key and go to 2D, 3D. In there, in the equation, down arrow by 1, I want to edit that, edit, and in there I will paste what is in the buffer. Redshift, paste. That is the expression I want to plot. Enter and enter to get out of there. And then again, Shift key, press and hold the Windows menu, this one. In this one we specify what is the range that we will use for plotting. On the horizontal axis is going to be from 0 to 10. And on the vertical axis, I don't really know what scale I should use, so I'm going to ask the calculator, do an automatic computation for the right scale of the vertical axis. I'm ready to erase the previous plot and draw a new one. And that is a solution. You say, well, I would like to see a few more cycles of oscillation. No problem with that. Let's go back and change the range from 0 to 40. Erase and draw. And that is the solution to part C. How that current in the inductor oscillates between 1 amp and 7 amps permanently after an initial transient period dictated by the time constant of this exponential. After 5 seconds, the steady state is a sinusoid with a frequency of 1 radians per second according to that oscillates between 1 amp and 7 amps. That is the current in there. Last, we need to determine what is the value of that current at t equals 1. Now I want to evaluate this expression at t equals 1. That is, x has to be equals to 1 here, there, and there. A quick way of doing this is this one. I create a variable with the value 1 and give it the name x. 1, enter, apostrophe x, store. Now there is a variable, look, this variable x that has a value 1. You're not sure? Click, you see, it has a value 1. Now, when I ask the calculator to evaluate this expression with the eval key, I get this expression. It has replaced x by 1 everywhere, but we want a numerical expression, sure. Redshift, numerical value of that, and I get 2.85 amps. And with this, we complete the solution to this exercise. The current in that inductor flowing from left to right at t equal 1 second is 2.85 amps. That is the solution to the exercise, but not the only one, not the fastest one. No, we used brute force. Let's solve that a second time in a more efficient manner. Using superposition, we have two sources. We identify the circuit that each one of them sees separately. In this case, we eliminate the current source. In this case, we eliminate the voltage source. And then we find the contributions to the current in that inductor by each one of the sources. We compute this current, the contribution of the V source to that current. That current is simply the value of the source, 2 over S plus 1, divided by the sum of those two impedances. That is this current, after some simplification. And the contribution of the current source is a current divider, this current. Observe that the inductor and the capacitor in this circuit are in parallel. They share this node here, and they also share this node, which is the same one. So you see they are indeed in parallel, and the current here in this inductor is 4 over S, that multiplies 1 over S, divided by the sum of 1 over S plus S, a current divider. So that is this component over here. We add them together, we simplify, and obtain the current in the inductor that we're looking for. Simplifying, we get exactly the same current we had before in a much, much faster manner. The rest of the solution is the same as before. But this is not the last of the possibilities, no. Let's solve that using M&A again, but this time taking advantage of that evil branch and call it an angelic branch the way we did in the first term, because that branch can help us. Observe, if I choose this one as my reference node, which is what I did before, the reference, the negative of one evil branch, Then the voltage on this other node is not unknown. I don't need to write a KCL equation for that one. I say if this is my reference, the voltage of this node is the value of the source, 2 over S plus 1. And then I have only to worry about the other two nodes, nodes 1 and 2. And we write equation. As soon as I write a KCL equation for node 1, which is 4 over S, currents entering, and this one equals to the currents, this one, V1 divided by S, plus this current, which is V1, minus the value of the voltage of this source given by this expression divided by 1 over S, this one, we realize one thing. Hey, wait a minute. This equation has only one unknown V1. I don't need any more equations to solve for V1. What's more, V1 divided by S is the current I naught. So I only need one equation, and that is the one we solve. We go to the calculator. But before doing that, I always click the mode key and then goes to the CIS to check in the CIS that each one of those radio buttons is unchecked. So all of that is clear before I proceed with typing the equation. Here is the equation. I also observed one more thing. Observe the independent variable that we saw before. This one is the same one I'm using as the Laplace variable. So instead of S, I'm using x in my equation. I solve that one as a system of one equations with one unknown for the variable V1 with the linear solver, with this one. And that is the solution. V1 is that expression. Remember, x represents the Laplace variable S. Well, that voltage divided by S, the impedance of the inductor, gives us the current I naught. Well, we only have to multiply the denominator by x. 2s squared plus 4s plus 4 divided by x to the fourth plus x to the 3 plus x squared plus x, which is exactly the solution we had before. The rest of the solution remains the same. Thank you very much.